Today's lesson starts us with topic 3.3, which is about differentiating inverse functions or finding the derivative of inverse functions. We're going to start off with, well, actually, let's back up just a moment. And what I want us to notice here is with the learning objective. Sorry about that. Your job by the end of this lesson is to be able to calculate derivatives of inverse and inverse trig functions. So we'll do inverse trig functions in 3.4, and we're just going to look at general inverse functions right now. Basically, what we're going to do here is learn a formula for finding the derivative of an inverse function, but it's also possible to derive that formula if you ever get stuck and don't remember it. But hopefully we'll use it enough times that it'll be fairly simple. So let's start for a moment just remembering what an inverse function is. So if we have two functions, let's say we have the function g and we have a function f, and we can say that g is the inverse of function f if and only if f of g of x equals x. Now, this is a composite function where we have taken g of x, so we've got f of, and we've plugged g of x into f. And if that equals x, and also if g, let me back up and do a different color. If g of, and then we plug f of x in, equals x, then we have inverse functions. The idea is that inverse functions undo each other. So technically, what's happening here for all intents and purposes is that f and g are canceling each other out. So f and g are canceling each other out, and g and f are canceling each other out. Okay. A few of the things to remember about inverse functions, and we'll get to those in a little bit, but one is that one of the ways we denote the inverse function is f with this little -1 exponent. But the thing I want to be real careful about is this actually is not an exponent. So not an exponent is just a superscript. It does not mean 1 over f. Okay. Instead, this is read f inverse, and it indicates the inverse function of f. Okay. Some properties of inverses. If g is the inverse of f, then f is also the inverse of g. The domain of the inverse is equal to the range of the function and vice versa. So let's look at a graph real quick. Let's say for just a moment that we have the graph of f of x. And let's say it just happens to look like this. Okay. We'll call this f of x. And we'll say it has the point 2, 4. It goes through 2, 4. So we would say that f of 2 equals 4. Okay. The inverse function, the domain and range reverse. So the inverse function looks like this. It's actually a reflection. They are reflections over the line y equals x. So this is f inverse of x. And it has the point 4, 2. So that f inverse of 4 equals 2. That's going to be a really important concept to know when we are trying to find the derivatives of inverses. Okay? The last property is that not every function has an inverse, but if a function does have an inverse, then it only has one inverse. It can't have multiple inverses. All right, so we're going to look at example 1 here. We are given two functions and their equations. So f of x is x cubed. F inverse of x is the cube root of x. That's kind of obvious that cubing and doing the cube root are actually inverses of each other. They do undo each other. But knowing that that's what those are, we're going to do some work here. So for a, b, and c, it wants you to find f of 2, f prime of x, and then f prime of 2. So you're going to use f of x for these over here. And then d, e, and f want you to find those same things, but of this function here. So f inverse of 8, the derivative of that inverse function, and the derivative at 8. If we're going to have to find the derivative of this function, we want to make sure we rewrite it as a power. So f inverse of x is x to the 1/3. I'm going to stop this video, and you go ahead and work through A through F, and go ahead and answer the question at the bottom, what you notice about your answers to C and F, and we'll pick up at the start of the next video.